Hello, in today's lesson we'll be reviewing the theory of transformers. If we look here on the screen, we have a couple of different transformers. This is a power distribution transformer like you would see in the small neighborhood. This is an isolation transformer like you would see in an electrical panel. On the top here, maybe you can see it, maybe you can't, but there's a electrical schematic. And what we're going to talk about today is the theory of transformers. Our objectives for today, we'll go over the theory of operation of transformers. We'll look at key terms that are associated with transformers. We'll talk about transformer action. Then we'll talk about transformers' voltage, current, and power relationships. All right, the first thing that we're going to do is we're going to talk about the theory of operation for a transformer. Before we get started on that, we want to review magnetism. If we remember, from our lessons on magnetism, if I take a magnetic material, let's say like a steel bar here, so I'll draw a picture of a steel bar. So this is steel or iron or something like that. And I take a wire and I wrap it around the bar. So here I have a wire and I put some turns around the bar. And I connect this to a DC power supply. We remember from our electromagnetism lecture, if I use the left hand rule, I would have current going in this way, and if I follow with my hand, what we would find is that we get a north pole here and we get a south pole here. If I took another magnetic material, let's say like a screwdriver out of my toolbox or something like that, and I set it next to here. So let's say this is a piece of iron, and I set it next to the magnetic field. What will happen is that I'll get a north pole in the piece of iron and a south pole in the piece of iron. Now, how does this relate to transformers? Well, we don't use DC with transformers. So if I go back and I erase this power source and I put in an AC power source, so what I'm going to do is I'm going to put in a AC power source. Now what's going to happen is when the sine wave goes positive, we would get a north pole and a south pole. And when the sine wave goes negative, we'll draw that in a different color here. When the sine wave goes negative, we would get a south pole here and a north pole here. And this is what we would use to demagnetize. So if I had a piece of iron that was magnetized, what would happen is this would become demagnetized. Now, if I put another coil of wire on the bar, so let's draw that in. So let's say here we put another wire on this bar. So here's some turns for this, and what will happen is as this magnetic field goes from a north pole to a south pole from the bar back and forth, current will be induced in this other loop of wire. And so if I took and put a load resistor between these two wires, what would happen is that the magnetism that was created from this loop of wire would induce current to try to turn this loop of wire into an electromagnet, which would cause current to flow. And if this was a light bulb, what would happen is we would see AC current flow through the light bulb, and the relationship between how much voltage we apply in this electromagnet and the voltage that is seen on the light bulb is going to be determined based on the number of turns. So as we get to talking about some of the formulas, things that are going to be important are going to be the the number of turns, oops, try that again. The number of turns for this one, that would be in the primary. And then also the number of turns in the secondary. So one of the things that we're going to talk about today is that the part of the transformer that gets supplied voltage, that's the primary, and the part of the transformer that that induces the current and is connected to the load, that's the secondary. So for this whole lesson, every time we're talking about transformers, the primary is always connected to the supply, and the secondary is always connected to the load. All right, so let's look at maybe a little bit of a better drawing of this. So here is an example where we have a bar and then we have a coil of wire. Now you'll notice in practical transformers that they use a lot of turns in order to make this work properly. And so here we have a primary coil, and what they're showing in this example is that this is a DC source. So when the switch is closed, we create a electromagnet, and as the electromagnet is kind of charging up, we induce current in the secondary coil. So that's what they're kind of showing here. So when they close the switch, we get current induced, and this is a voltmeter, and so it's showing that in the secondary we're generating a voltage. When the switch is opened, what happens is the magnetic field collapses, and we see a change in the magnetic field where the magnetism is going down, and then the current is induced in the opposite direction. So all right, so let's look at some key terms here. The first thing that we're going to talk about is the primary. We talked about this a second ago. The primary is the coil that is attached to the source. So later on in this in these lessons, we'll start drawing transformers like this. This is the electrical schematic of a transformer. This is what we would see on our electrical schematic. We'd have a power source connected to the primary. So this would be our primary right here. And we can talk about the primary. It's a coil and it's connected to the source. The secondary, that is here, oops. And that's going to be connected to the load. And so what we'll find is when we start looking at our transformers that we're going to have a load connected to it. Here I'm showing it as a resistor. So we have a primary and a secondary on all of our transformer problems. The secondary is also a coil, and it's connected to the load. So whatever the load, if we're trying to turn on a light bulb, or we're trying to connect from the power lines to a house or something like that, the secondary is always connected to the load. The next thing that we have are turns. So when we make a primary coil, the way that we're going to make it is we're going to make it by wrapping wires around a block. So here in my first example that we had, this is the turns. So this one is a very simple example. It only has, looks like 3 turns in the primary, and then there's 2 turns in the secondary. So this, when we look at the turns, what we're talking about is the, if we have a block here, I'm not very good at drawing these, but so we have a block. How many times do we wrap the wire around the block? Those would be the turns. Ratio, we're going to start talking about ratios. As we look at how the transformer operates, it's going to operate based on ratios. The way that I would usually think about this would be an example of like a two wheels connected by a belt. So let's say I have a wheel here, and then I have a bigger wheel here, kind of like a bike chain. And let's say that I drew these perfectly to scale, and this one has a diameter of 1, and this wheel has a diameter of 2. So what would happen is I'd have to turn this one around. If I turned that wheel one whole revolution, the other wheel would go about halfway around. So I'd have to turn this one around twice to get this one to turn once, because this one has twice the diameter. So we could say that this is a if we were talking about this in terms of how the ratios, we have to turn this one 2 times to get this one to turn 1. So this would be a 2-to-1 ratio. When we start talking about ratios on our transformer, we're also going to have things like that. So if I make a number of turns on my primary of, let's say, 10, and the number of turns on my secondary is 5, I would also end up with a 2-to-1 ratio. Now, when we look at ratios, what we're talking about is it a 2-to-1? Is it a 5-to-1? Is it a 10-to-1? What we're going to find is that that's going to be related to the voltage and the current in the transformer. The next thing that we're going to talk about is taps. So when I have a coil of wire, so let's say that I have a really long coil of wire, so I'm kind of saying, pretend like these are all my turns. When we get to more advanced transformers, what happens is they'll have multiple taps on the transformer. So maybe we could make a connection to the transformer and cover the entire transformer. So that would be all of the number of turns. So let's say that this has maybe 50 turns. If the transformer has what's called a center tap, that would be a connection to the middle. And if we go between the center tap, let's call this one A and this one B, we would have 25 turns here, and we would have 25 turns here. And this will allow us to get different voltages off of the transformer. So taps are connections to the transformer coil in different positions. All right, so in order to have a transformer, we need to have 2 coils minimum. We could have a transformer with more coils. We have a primary and a secondary. The primary is connected to the source. The secondary is connected to a load. The way that transformers work is through what's called mutual induction, which means that when we have a varying magnetic field near a wire, it will induce current in the wire. And in order to optimize that, we put the same 2 coils on the same core. We'll look at some practical constructions here in a minute. Transformers do not have moving parts, so there's nothing to wear out. They last for a very long time. They're very efficient. We can get transformers that are, maybe 96 to 98% efficient, which is pretty good. And they're very low maintenance. Many of you who are working in maintenance, you probably rarely go and fix a transformer. Usually the only thing that could happen to a transformer is it could blow up or it could, fail. All right, so here is a practical transformer. So this is kind of a visual of what a transformer would look like. A lot of times they're made using this construction. Somewhere on the transformer, it'll tell you what's the primary and what's the secondary. Usually that's on either a data table or a label on the transformer. And if on the transformer, what we would be seeing is that this big thing here is the loops of wire. And so a lot of transformers are made in this kind of figure 8 configuration for the core. So this is the core of the transformer. Usually they'll make that using iron with laminations. And then there's a primary winding, and then there's a secondary winding. And so in the primary winding, we'll see the turns. So you can see these wrapping around the transformer. Those are the turns in the primary. And then we have some turns in the secondary. This would be our electrical schematic for that. So we'd have an AC source. We start getting into the transformer problems. There'll be a source voltage. Maybe let's say for this one it's 120 volts, and then we have a transformer, and then the transformer is used to match. So the source is 120 volts. Let's say in this example that this light bulb needs to run on 24 volts, and again this would be AC. We can't use DC with the transformer unless we make a really fancy circuit, which is beyond the scope of this class. So the light bulb has to run off of 24 volts. If we plug it into the outlet, the light bulb will explode, it'll burn up. And so what we do is we put a transformer in between, and it takes the 120 volts and steps it down to 24 volts so the light bulb could operate effectively. The primary coil on our transformer converts the electrical energy to magnetic energy. It transforms the current and voltage into an electromagnet. That electromagnet is then on the secondary converts into the electrical energy on the for the light bulb. So what goes into the transformer, we'd have voltage and current going into the transformer. Now if you remember, power equals voltage times current. So we have power going into the transformer, electrical power, and then coming out of the transformer, we would have current and voltage coming out of the transformer, which means that we would have power coming out of the transformer, and that power would be used by the light bulb. Here's another example of it, just kind of demonstrating that we have the primary over here connected to the power supply, and then we have the load over here connected to the secondary of the transformer. Inside a core, if we used a solid block, we could get what's called eddy currents. Eddy currents are a type of current that obstructs the efficiency of the transformer. And so the reason why we care about eddy currents is the reason why the blocks, when they make the transformers, if we go back up here and look at the transformer, you'll always notice that they have these laminated plates. The reason why they have the laminated plates is for the eddy currents. And so the laminations reduce the amount of eddy current flow by limiting the path of the circulating current. So we don't want the current that goes, that's induced in the core to, if we had our core here like this, we don't want the current, and the current's always going to take the path of least resistance. That doesn't mean that it would be the best for the efficiency of the transformer. We don't want the currents kind of going around the outside of the transformer this way, because that would mess up our efficiency. So eddy currents relate to why we always use steel laminations. All right, so here's an example of an ideal transformer. So we have a wall outlet here. So we have 120 volts. We have a, looks like we have a doorbell here, and the doorbell needs to operate at 15 volts. When we look at the transformer, the way the transformer is going to work, the power going into the transformer is going to equal the power coming out. And so what we'll notice here is that we have voltage and current going into the transformer, and then we have voltage and current coming out, and they're going to follow this relationship. And so that means that the voltage and current in the primary equals the voltage and current in the secondary. So in this circuit, if I took the power in, so the power in equals the voltage in the primary times the current on the primary. That's where this comes from, 120 volts times 0.625 amps. The voltage on the secondary times the current on the secondary, that would be the power out. So power out would equal the voltage on the secondary times the current on the secondary. And so for this example, we'll notice that it's 75 VA. Now's a good time to talk about when we have power for transformers. They're always going to be denoted in VA. Now for this class, we're going to say that a VA is equal to a watt. So the VA is the unit. So this is the unit. So we'd say, how big is our transformer? It's 75 VA transformer, or it's a 1.5 kVA transformer. This type of transformer, that would be the power rating of the transformer. So when we're sizing the transformer to see if the transformer is big enough, can it handle the amount of current that we're trying to push through it, it would have a power rating. The unit that we're going to use for power in transformers is VA. And we're going to assume in this class that that's similar to a watt. When we get to later classes, AC, electrical power, has a couple of different ways to measure it. One is VA, one is watts, one is VARs. We're just going to assume that a VA equals a watt for this class. All right, so let's look at a couple of things. So we have a couple of definitions here. The first thing that we're going to notice is that we have these equations here. So let's look at, for these equations, what these terms mean. So the first thing that we have is VP, VS. So let's look at that first. So VP, now this is a little confusing because in the last lesson, VP was voltage peak. For this class, for transformers, this is the voltage of the primary, which is the supply voltage. The VS, that would be the voltage here, which is the voltage of the secondary. And then we have NP and NS. NP, a lot of times I'll put this up here. NP is this is the number of turns in the primary. And then we have NS, which is the number of turns in the secondary. And then I think I'll do these in a different color. Then we'll have the IP, which is the current in the primary. And then we have the last term here is IS, which is the current in the secondary. Barely fit it in there. Okay. All right. So for our transformer problems, what we're going to find is that there is a ratio between the number of turns in the primary and the number of turns in the secondary. So if we know the number of turns in the primary and we know the ratio between that and the number of turns in the secondary, that's going to be equal to the voltage in the primary ratio to the voltage in the secondary ratio. And it's going to be also equal to the inversion of the current. So that's the current in the secondary to the current in the primary. So let's put some numbers on here to try to understand what's going on. So let's say that for this problem, the number of turns in the primary is 100. So we'd have 100, and the number of turns in the secondary, let's say, is 50. So that means that the ratio between the number of turns in the primary and the number of turns in the secondary would be 2 to 1. So the way that we'd figure that out is we just divide the bigger number by the smaller number, and we get 2 to 1. So that means that the voltage of the primary to the voltage in the secondary is also going to be 2 to 1. So if the voltage in the primary, let's say, was 100 volts, the voltage in the secondary would have to be 50 volts. These ratios have to be maintained. And if the current in the secondary, let's say that the current in the secondary was 2. Well, 2 is a bad example. Let's say that the current in the secondary was 10. So the current in the secondary is 10. We have to maintain that 2 to 1 ratio, so that means that the current in the primary would have to be 5. So that way we still had a 2 to 1 ratio. So when we solve these problems, the basic formula that we're going to use is that the power in has to equal the power out. And so that means if we have current and voltage of the primary, that has to equal the current times the voltage in the secondary. And so these ratios, this 2 to 1 ratio, is going to have to be maintained. And so when we solve the problems, what we're going to do is some of the items will be given, maybe the number of turns, maybe the voltage, maybe the current, and then we'll have to figure out the rest of them based on the turns ratio. All right, so let's look at some more examples, kind of back up a little bit. So let's say that in this circuit we have 8 turns on the primary and 4 turns on the secondary. So if we supplied an 8-volt AC supply here, what we would see is that each turn would be worth 1 volt. So we have 8 volts total, so each turn is going to get 1 volt across it. So for this transformer, if we looked at the ratio, we have 8 turns to 4, so this is going to be a 2 to 1 transformer. So that means that on the secondary, each turn is going to get 1 volt. So on the primary, the way that we set this up, and this one is set up this way just for so you can visualize it easily, each turn is worth 1 volt because that's what's supplied. So every turn that I have on the secondary also gets a volt. So if I have 8 turns and 8 volts, every turn in this transformer is going to either use 1 volt or generate 1 volt, which means that we'd have 4 volts AC on the secondary. If I change this voltage supply to be 16 volts AC, the 2 to 1 would still, because that's the way the transformer is made, now I would have 2 volts on each one of the coils, which means I'd get 2 volts on each one of these, I shouldn't say coils, I should say turns. So that means that the secondary voltage then would change to 8 volts AC. So in the lab, if we had this transformer, we had a variable supply, we could test out all different values for the peak voltage, and we would get all different values on the secondary. All right, so let's look at another transformer. Now we'll notice that this one has a few turns here, and it's got many turns over here. Now this isn't exactly drawn to scale, but we have a transformer that has 50 turns on the primary, and then it has 100 turns on the secondary. So this would be, the way that I would calculate this is that I would take 100 divided by 50, and I'd end up with a 1 to 2. There's twice as many turns in the secondary. So if I supply 120 volts, I must get 240 volts out to maintain the 2 to 1 ratio. It looks like I drew this right in the way of the slideshow, so let me get this out of the way. So the turns ratio here, the author in the textbook, a lot of times they use the turns ratio to do this. That's not my preferred method. I don't like using it that way. I like doing the turns ratio as 50 to 100 or 1 to 2 rather than do a fraction. Some of you that have had me before, we always talk about how we don't like using fractions. If the voltage on the secondary then has to be twice the voltage on the primary. Oops. All right, next problem. So we have 240 volts on the primary. We have a number of turns, 105. So what we need to do for this one, we'd start off with 100 to 5. So that would be 100 divided by 5 is 20. So I'd have a 20 to 1. So this transformer, we haven't talked about it yet, but we'll start using this term. This would be a step down transformer. The voltage is going down. We know that because there's less turns over here. So if I have 240 on this side, I got to maintain my 20 to 1 ratio. So the voltage on the secondary would equal 240 divided by 20. So that would be 12. So that means that I should have 12 volts on the secondary. I think for this one, my drawing stuff is going to be in the way. I'm going to erase this. So we look here, and we have the turns ratio of 20 to 1. This is the part that I like to use, not the fractions. And that means that we would take in the 240 volts and divide it by 20, and we would get 12. Here is another example of a transformer. Now this is a unique transformer. This one has, this transformer has multiple taps. So when we have a transformer that has multiple taps, there's a certain number of turns for the whole transformer. And they're saying here that that's 1,200 turns for the whole transformer. Now when we have taps, what that means is that we could connect to a different spot in the transformer and get different amounts of turns. And so if we connected to this tap on this transformer, it's saying that we would have 1,040 turns, and if we connected to this tap, we would have 600 turns. Now this type of transformer is used when you don't know exactly how the person that you're selling the transformer, so if we're working at a company that was manufacturing transformers and we wanted to sell one transformer and you always wanted to get 24 volts out of the transformer, depending on your customer, they could supply 240 volts and connect it here. So if they had a 240 volt supply, the ratio would be 1,200 to 120 if they connected it to the 240 volt tap. So let's say we connected it to this tap, which means that we would have, what would that be? That would looks like it would be 10 to 1. If we connected it to a different tap, so let's say that we wanted to connect to the 208 tap. Okay, so now we connect to the 208 tap. What's happening now is now we have a different turns ratio. Now it's 1040 to 120. So now we're getting a different ratio on the same transformer. So if I go to my calculator and I punch in 1040 divided by 120. I get 8.67. So that means I would have 8.67 to 1 if I connected to that tap. If I connected to the 120 volt tap, so let's say that I connected here, now I'm going to get another different ratio for this transformer. This would be 600 to 120. So if I took 600 divided by 120, I get 5. I probably should have been able to do that in my head. So I'd have 5 to 1 on here. So with this transformer, what the taps allow me to do is, if I have taps, what happens is I can get different ratios. So I have one transformer, but I can get 3 different ratios. And so depending on my application, you know, if I'm trying to get a transformer to always have 24 volts out, I can connect 120 and get 24, I can connect 208 and get 24, or I can connect 240 and get 204. And the way that it works is by changing the number of coils that we're connected to, or I'm sorry, the number of turns that we're connected to in that primary coil. We could also have the same thing on the secondary. So again, we have a transformer that has multiple taps, and this time the taps are on the secondary, so we always supply 120 volts, but we can get either 12 volts or 24 or 48 volts. And so with this type of transformer, we can get multiple output voltages with a single input voltage. All right, so let's look at another example. Here we have a transformer. The turns ratio is 1 to 5. So I'm going to write that over here. So I have a 1 to 5 transformer. Oh, shoot, let me get this out of the way. And it looks like we have 60 volts and 125 ohms. So the current in the secondary, so when we're trying to find the current going here, we would take 60 volts divided by 25 ohms, and we would get 2.4 amps. Now, we need to remember that when we have a turns ratio of 1 to 5, that means that the current ratio is going to be 5 to 1. That means we're going to get 5 times as much current on the primary as on the secondary. So that means that we need to multiply the secondary current, the 2.4, times 5 in order to get the primary current, which should be 12 amps. So if I draw this over here, I'd have 12 amps here, and I have 2.4 amps. What we'll notice on this transformer is that the current goes down. That means that the voltage needs to go up. So if we had 60 volts here, then this would be 60 divided by 5, which would be 12 volts. So we would have 12 volts to 60 volts. This is a step-up transformer, which means that the current would go down. These two are going to be inversely acting for the transformers. We're just going to ignore this one. I probably should have deleted that slide. The next one that we're going to look at is what we call a center tapped transformer. Center tap means that one of the taps is connected in the very center of the secondary. This is the center tap, and it's also grounded, which means that this is at 0 volts. So if we look here, what I'm going to do is I'm going to draw this sideways here. So here's my transformer, and this is not drawn to scale. So here is a diagram of this one. Okay, so let's say that, let's pretend that there's a person. So here's a person, a little stick figure. Okay, and they're standing on the ground. And the reason why we use a center tap transformer, why we care about where we ground the transformer, is if they're standing on ground and they decide that it would be desirable to touch one of the wires. So let's say that they touched just this wire and they're standing on the ground. What we would see is that they would have approximately 120 volts between the ground and this tap. So on here we have 120 volts between ground and this tap. So they would be, if they were touching this, they would get 120 volts. So we'll do this in a different color. Let's say that instead, so we have, or maybe we'll say this, we'll have another person. Okay, so now here we got another person, and they're going to touch this tap. They would also have 120 volts between here and here. Okay, we have 120 volts between this tap and ground. So this would be like if you stuck your one finger into the outlet, that's what you would feel. It's not very pleasant, but it wouldn't be super terrible. Now, if you decided to, let's say, connect yourself to the circuit in a less desirable way. So let's say that so now you're this person here, and you decide to connect between both wires. Now you're looking at 240 volts, which is why if any of you are ever working inside an electrical panel in your house, or you take the cover off your breaker box, you want to be real careful to only touch it with one hand. 240 volts across your body, that's going to be really bad. That would be potentially cause death. And so a lot of times when we deal with transformers on the secondary, we're going to pay attention to where we ground it, and what we're worried about is the potential for somebody who gets electrocuted. And there's some kind of best practices that we would go through in other classes as we were designing these systems. Transformer terminals, if we had a transformer sitting in front of us, we would see that there'd be letters next to the screws, H1 and H2 for the high voltage leads, and then X1 and X2 for the low voltage leads. Now, if there was more taps, or there was more coils on the transformer, we might see things like H3, H4, H5, H6. On the secondary, we might see X3, X4, X5, etc., depending on how the transformer is wound and how the transformer is tapped. Here's an example of a transformer. This one has two coils, and then we're showing a jumper between H1 and there's a jumper here between H2 and H3. This is the type of transformer that would be slash rated. So in other classes, this transformer would be a 240 volt slash 480 volt transformer on the primary, and on the secondary we would have 120 volts on the secondary. And then what you do is, these aren't connected. These two coils, H1 and H2, and H3 and H4, are two separate coils, and we'd connect jumpers either to get 480 volts or to get 240 volts. Right now they're showing the 480 volt jumper. All right, that's the end of this lesson. Thank you.